Hello everyone, welcome to this lecture. So, in this lecture we will now start from this lecture onwards we will start discussing about the BGW protocol for perfectly secure MPC, and we start first with the simpler case, namely we consider the case when the underlying function is represented by a circuit consisting of only linear gates. So, let me quickly go through the idea behind the BGW protocol, namely the principle of shared circuit evaluation. So, imagine you have some circuit which is publicly available, the circuit is over some finite field, and in the system there could be up to t number of Byzantine corruptions, malicious corruptions, where t is up to n over 3. Now, I stress that this condition t less than n over 3 is a necessary condition for any perfectly secure multi-party computation, and we can very easily prove this. What we can say here is that the Byzantine agreement problem is a special case of MPC, and we had already proved that for perfectly secure Byzantine agreement the condition t less than n over 3 is necessary. That automatically shows that for generic functions, for computing any generic function, arbitrary function, abstract function with perfect security, we require the condition, necessary condition t less than n over 3. So, there will be various stages in the BGW protocol depending upon what gates you are evaluating. So, we start with the input stage where all the inputs for the function are made available in a secret shared fashion using a NT secret sharing scheme based on polynomials, and for doing that we will use polynomial based VSS, the VSS schemes which we had discussed till now. So, we can use the VSS scheme with t less than n over 3 which we had discussed earlier, and now each party is going to do the following. Say for instance, we take the party P1, it owns the input x1. So, what it can do is it can act as a dealer, okay, and take x1 as its secret and run the sharing phase protocol for secret sharing the value x1 in an NT secret shared fashion. Okay. Due to which at the end of the sharing phase protocol every party will have a share for the value x1, and it will be verified during the sharing phase protocol that indeed party P1 has secret shared some x1 using a t degree polynomial. That verifiability comes because of the strong commitment and the correctness property of the verifiable secret sharing scheme. So, even if P1 is corrupt, even if it is a corrupt dealer, it cannot distribute arbitrary shares for its input x1. The shares which it is going to distribute to the honest parties, they are going to lie on some t degree polynomial, and that is guaranteed because of the strong commitment property. In parallel, in the same input stage, party P2 is going to act as a dealer and run or invoke an instance of the sharing phase protocol of the polynomial based VSS to secret share its input x2, due to which every party will now have a share of the input x2. Similarly, the third party will act as a dealer and invoke the sharing phase protocol of the VSS scheme to secret share x3, and similarly party P4 in parallel will invoke the sharing phase protocol to secret share the input x4, and that will complete the input stage of the protocol, at the end of the which all the inputs will be NT secret shared. If the dealer is honest, then it will be also additionally guaranteed that the NT secret sharing is a random secret sharing, namely the probability distribution of the shares corresponding to the corrupt parties in that instance will be independent of the underlying secret which has been shared by the honest dealer. So, for instance, in this example I am considering P1 to be corrupt. So, P1 will be knowing all the shares of x1 because it itself is acting as the dealer, but the share which it receives for corresponding to x2, x3, x4, they will be independent of x2, x3, x4. So, P1 will completely be clueless what exactly is x 2, what exactly is x 3 and what exactly is x 4. Now, once the input stage is over, the parties go to the computation stage where they start evaluating each gate in the circuit in a topological order by maintaining the BGW gate invariant, and the gate invariant is the following. If the inputs of the gate are NT secret shared, then through the steps of the BGW protocol it will be guaranteed that even the gate output is randomly NT secret shared among the parties. Now, maintaining this invariant may require communication, interaction among the parties, or it may not require interaction among the parties depending upon the type of the gate. So, again what it means here. So, in the topological order, suppose this is the first gate. Okay. So, everyone will try to evaluate this first gate, which is the addition gate, and currently the inputs for this plus gate are x 1 and x 2, but no one knows the value of x 1 and x 2 completely. Of course, the respective input owners, they know the values of x 1 and x 2, but rather what we can say now is that the inputs x 1 and x 2 are currently secret shared. So, as per the steps of the BGW protocol, the gate invariant will guarantee that after the evaluation of this plus gate, every party obtains a share for this for the output of this plus gate, namely P 1 will have a share I 1 1, P 2 will have a share I 1 2, P 3 will have some share I 1 3 and P 4 will have some share I 1 4. So, that together I 1 1, I 1 2, I 1 3 and I 1 4 constitute an NT secret sharing for the value I 1. Then the parties go to the next gate and they evaluate it using the steps of the BGW protocol, and at the end of the evaluation of this gate, every party will have a share corresponding to the output of this gate. Then they go to the next gate, okay. And then again the invariant will ensure that every party obtains a share corresponding to the output of this gate, and then they go to the final gate, and again by maintaining the invariant they obtain a share for the output value. Okay. Now, once all the gates are evaluated, the parties go to the output stage where now every party can make public its share corresponding to the output of the function. There could be up to t parties who may make public incorrect shares, and the identity of the corrupt shares may not be known. So, what the parties can do now is that they can apply the Reed-Solomon error correction, and they will try to reconstruct the correct output y and terminate the protocol. Okay. So, the BGW protocol uses the polynomial based NTVSS, the verifiable secret sharing scheme based on polynomials, because of its linearity property. So, what exactly is this linearity property? Let us quickly go through it. So, if we are using any polynomial based VSS scheme, then it guarantees the correctness and a strong commitment property. The correctness guarantees that the shares of the honest parties lie on some t degree polynomial, and a strong commitment property also guarantees that the shares of the honest parties at the end of the sharing phase also lie on a t degree polynomial. Okay. That means, if some value is secret shared using this polynomial based VSS, then irrespective of whether the dealer for that sharing instance is honest or corrupt, the shares of the honest parties are guaranteed to lie on some t degree polynomial. So, now imagine there is some value s which is NT secret shared. When I say NT secret shared, means that there exists some t degree polynomial whose constant term is that value which is shared, and every party has the value of that sharing polynomial at alpha I. Okay. Namely, the party Pi, sorry, to be more precise, the party Pi has the value of that sum is sharing polynomial at alpha I. So, say there is some value s which is secret shared in this fashion, and say the underlying secret sharing polynomial is a polynomial which is a t degree polynomial, and suppose there is some value c in the field which is publicly known. Now, if every party just multiplies its share of S with this value C. And then if we focus on the resultant vector of shares, this resultant vector of shares constitute a vector of shares lying on a t degree polynomial. That t degree polynomial is C times the A polynomial. Why? Because if we evaluate this new polynomial at alpha I, we get the ith component in the new vector. And what will be the constant term of this new t degree polynomial? The constant term of this new t degree polynomial will be C times the constant term of the A polynomial. The constant term of the A polynomial is S. That is why the constant term of this new t degree polynomial is C times S. That means the new vector of shares actually constitutes a vector of NT secret sharing for the value C times S. In the same spirit, if we have if we have a value S which has been secret shared using this polynomial based VSS, and if there is some value C from the field and every party adds now its respective share of S with the value C, then we obtain a vector of values where the party Pi will have the ith component of the vector, and together this vector now constitutes an NT secret sharing for the value C plus S, because this new vector of values lie on a new t degree polynomial, namely this polynomial A plus a constant polynomial C, and the constant term of this new t degree polynomial is C plus S. And finally, if there are two values S1 and S2 which are secret shared through t degree polynomials A and B, and every party just locally adds its shares of S1 and S2, sorry, not S1 and S2, my bad here, the secrets are S and S prime. So, if every party locally adds its respective share of S and S prime, then that will give that party its share of S plus S prime, because together this new vector of values lie on a new t degree polynomial whose constant term is S plus S prime, and ith party will have the ith component of this new vector. So, this is what is linearity property. What this shows here is that if you have a value or more than one value which is secret shared using a polynomial based VSS in an NT secret shared fashion, and if you want to compute some linear function of those secret shared values, then you can compute that non-interactively. Namely, say for instance, if S is secret shared and S prime is secret shared, and if there is an addition gate in the circuit whose inputs would have been S and S prime, then during the BGW gate invariant the parties need not have to interact. Each party can locally go and add its share of S with its share of S prime, that will give that party its share of S plus S prime, and so on. That is what is the linearity property here. Now, by exploiting this linearity property, we can quickly get the following result. Imagine you have a set of parties connected by pairwise private channels, and imagine you have a function which is represented by and imagine you have a function which is now a linear function over the field, namely the function is of this form where C1, C2, Cn are publicly known constants, and this function is represented by the following circuit. Then there exists a perfectly secure MPC protocol which allows the parties to securely compute this function even if there are up to n over 3 computationally unbounded maliciously corrupt parties. Okay. And the protocol is very straightforward. During the input stage, every party will invoke an instance of the secret sharing phase protocol, okay, the sharing phase protocol of a verifiable secret sharing scheme based on polynomials. So, for instance, P1 will act as a dealer, it will run the sharing phase protocol of the VSS and say the resultant shares are x11, x12, x1n, which are distributed to the respected parties, okay, during the sharing phase protocol. In the same spirit, party P2 acts as a dealer, and this can happen in parallel. So, we do not need to depend or we do not need to wait for the VSS instance of party P1 to get over and then start the VSS instance for P2. No, all these VSS instances can be executed in parallel. So, in parallel P2 can act as a dealer with input x2 and trigger or invoke an instance of the sharing phase protocol of the polynomial based VSS, and that will ensure that its input x2 is NT secret shared. In parallel P3 acts as a dealer and does the same, and P4 acts as a dealer and does the same. Now, once all the inputs are secret shared, we have only one linear gate in the circuit. So, parties can use the linearity property and obtain their respective shares for the output of this linear gate, and then they can make public their respective shares of the output of the circuit. The corrupt parties may make public incorrect shares. So, what the parties can do is they can apply the Reed-Solomon decoding algorithm on the vector of shares corresponding to the output gate and reconstruct back the function output. That is a simple BGW protocol for linear functions. Let us do the quick analysis of the round and communication complexity. So, interaction is needed in this protocol during the input stage for verifiably secret sharing the inputs. So, the number of rounds in the input stage is basically the same as the number of rounds in the sharing phase protocol of the underlying VSS scheme, and the communication required will be n times the communication required for one instance of the sharing phase protocol. During the computation stage, no interaction is involved, and again interaction is involved during the reconstruction stage when the parties exchange their shares of the function output, and that will require the number of rounds which will be same as the number of rounds for the reconstruction function of the underlying secret sharing scheme. Okay. So, that is a very simple MPC protocol, perfectly secure MPC protocol for linear functions. In the next lecture, we will do an security analysis of the protocol. There are plenty of references for detailed description and a very rigorous formal analysis of the perfectly secure BGW protocol. My personal favorite is this first reference. Thank you.